What's up, YouTube? Welcome back to Gluten-Free Learning, and today we are doing Simpson's 1/3 rule, but we're going to check it out with multiple segments. So before, in my last video, we did Simpson's 1/3 rule, derivation, and example, but we only did single segment. So if you haven't checked that out yet, I'll send a link right now. Watch that video before watching this one. This one will make a lot more sense. But this basically is just a better approximation of our definite integral. So to describe what basically the multiple segment portion of Simpson's 1/3 rule is, let's just look at an example and compare the two and then come up with the formula that way. So if we're given a function, say x to the minus x times x, we want to evaluate that from 0.5 to 5. So then if we do a single segment, just like in my last video, we use the same formula, b minus a over 2 times f of a plus 4 times the function at the midpoint plus the function at the end point. So using Simpson's formula, this is what we get using the single segment. So you get 0.9762 for using Simpson's 1/3 rule with multiple segments. So the exact value, if you use your integration techniques that you know, like integration by parts, the exact value of the integral is 0.8694. Right, so that's not very good. Let's check out the error. Let's calculate our error involved. So the error with this is 12.3%. So that's actually quite high. So now what we want to do, we want to find a better estimate. And that's where using multiple segments come in. So if we've got our function f of x equals x e to the minus x, we want to now use Simpson's rule, 1/3 rule, to evaluate this from 0.5 to, let's say, 5. So previously we would just use the 1/3 rule with the single segment and we would just find the midpoint. That's what we did before, find the midpoint, evaluate the function at the beginning and the end, and add it to 4 times the function at the midpoint, 2.75. So, but now using multiple segments, in this case, n is going to be equal to 2, and we're going to apply Simpson's 1/3 rule twice. So we want to apply it to 2 different segments. So we're going to break this up and have 2 different integrals, basically. So by then saying we want to find the value of our integral from 0.5 to 5 of x e to the minus x dx, that is equal to, now we want to look at the first segment, and we are just considering this portion. So our upper limit in this case is going to be 2.75 and our lower limit will be 0.5. So when we do b minus a over 2, we have 2.75 minus 0.5. Sorry, over 6. And then that will just be times our f of 0.5. Now we want to find the midpoint. So 4 times our function value at the midpoint. So the new midpoint, midpoint number 1, that's going to be 2.75. The midpoint between 2.75 and 0.5 is just 2.75 plus 0.5 over 2, 1.625. So that's our new midpoint for the first segment. So then our function value at 1.625 times 4 is going to be the new middle point of the first segment. And then same as before, f of 2.75. So what we've done, we've just applied Simpson's 1/3 rule with a single segment on our first half of our interval. So now what we want to do, we're considering the second half of our interval, right? So we're looking at now from we're looking at from 2.75 to 5. This is our interval number 2. This is the second segment of Simpson's 1/3 rule. So we have to now add that to the first half. And now we've got to consider our new limits, right? Our new b is going to be 5, and our new a is 2.75 over 6. And then plugging that into our Simpson's 1/3 rule function, now we have to calculate a new midpoint. Call that x2. So x2 is 3.875. So that's the new midpoint of our second segment. So we plug that in, and then plus our function value at b, which is just 5. So this is literally it. That's what you have to do. You have to break up your function into two segments and apply Simpson's 1/3 rule twice. And let's see what that gives us. So we know that on the side here, so 2.75 minus 0.5, this equals 2.25, right? So that's looking at the first one, the first segment, and looking at the second segment, the multiplier outside the bracket is just 5 minus 2.75. And that also equals 2.25. So we can actually collect like terms, because these are both 2.25 over 6. So that's an important part in using Simpson's 1/3 rule for multiple segments. They should have the same multiplier outside of the brackets. And then we just have, you add them up. Okay, so we have 2.25 over 6. Now we need to sum the first segment plus the second segment. So let me just get this big long equation. And if we notice inside the brackets, we've got some like terms. So we've got an f of 2.75 and another f of 2.75. And if you notice, that is the midpoint of the entire interval. So we can actually rewrite this to say 2 times the function value of 2.75. Right? And then this will work for any number of intervals that you want. You're always just going to have, or you're just going to have a new midpoint for every segment that you've chosen. And in this case, we've got 2 segments, so therefore we've got 2 midpoints that we're dealing with, right? We have the 1.65 for segment 1, and then we've got the 3.785 for segment 2. So no matter how many segments you do, you're going to have that many midpoints, and you can choose infinite amount of intervals that you want, but you're just going to increase the accuracy of your estimate. So then this actually gives us, so we get 0.85900, which is definitely a better estimate. It's closer to our real value, and then this gives us an error of 1.2%. So just by increasing our segments by 1, we've actually made our error way better, because before, if you remember, our error was 12.3% using a single segment. So that was just basically using one interval and one midpoint from 0.5 to 5, and then we got a huge error. So using Simpson's 1/3 rule on multiple segments, all you got to do is remember to apply it 4 times. Apply it on however many segments you have, and then just sum up the 1/3 rules, the 1/3 totals, right? So we had 1 and we had 2, and what we did, we added those up, and we're always going to get on the outside, we're always going to get our multiplier is going to be the same. So we're going to be able to collect like terms, and inside the bracket will always be, we have 1 times the outsides, a coefficient of 1 times the outsides, and then the insides are going to alternate from 4 and 2. So if you want to write this down in kind of a formula way, we can say that I equals h over 3 times f of x naught. Now x naught is being the start of the interval, start of the whole interval. So remember, before 0.5 is the very beginning of our whole interval that we're interested in. So that's going to be the first term of this formula every time, plus 4 times the sum of the function at xi from I equals 1 to I equals n minus 1, right? And I equals odd, right? So if we look back at our original graph here, I said that the midpoint was x1, right? Because we had x x naught is 0.5, and then we had x1 as our new midpoint of this level. So we had 4 times first midpoint. And looking back up here, we had our 4 times the function value at x1. Right? So that's basically saying every midpoint of your segments, the function of that value is going to be multiplied by 4. So coming back up here, I've named this x2, but I guess for the purposes of this formula, that will be called, we can call it x3, right? We can say, okay, that's x3, because our midpoint of our entire function was going to be x2, and that would be 2.75. So if we're looking back up at the formula that we were using to calculate, we have 2 times the function value at 2.75. Right, so we have 2 times the function value at 2.75, which is the midpoint of our entire function, right? So that, and then that's also the same as saying 2 times the sum of our function value at xi when I is even to n minus 2. So that's saying basically the midpoints, or the midpoint of your big function, which was in our case 2.75, but if you're dealing with more segments, it's going to be just the midpoint or the start or ends of new segments. So in our case, since we were doing only 2 segments, it was the end of our first segment and the start of our second segment, right? So that's going to be the midpoint of the whole function. But if we were doing 3 segments, for example, then we would have 2 of these. We would have a start of at the end of the first segment and the start of the second segment, and the end of the second segment and the start of the third segment. And then you add that to f of xn. So that's going to be the very end value. And again, that's just, there's a 1 outside there. So this formula, I mean, you should do a couple examples before you can really understand this formula, but I would just stick to drawing out your picture and being able to pick out what segments or how you want to split up your segments, and then deciding or calculating your midpoints of your segments, and then just performing Simpson's 1/3 rule however many times you need to on however many segments that you create. So once you do that a few times and you get familiar with how this formula and function works, then you can kind of look at this the big formula, the big picture, and then just start applying them right away. And then remember that h, that equals b over a divided by n, n being the number of segments. And that is it. So thanks for watching, guys. We just did the derivation and an example of Simpson's 1/3 rule on multiple segments. So please, if you like my videos, subscribe to my channel, like my videos, share with your friends, and yeah, stay gluten free. Just kidding, I like gluten. Thanks for watching.